Hi, in this lesson, we're going to be going over the Unit 6, Lesson 7. The question here, are teenagers going deaf? What we're going to be covering is a two-sample z-test for P1 minus P2. This is a reminder that this is going to be the last template you're going to be working with for the state plan to conclude for this unit. And you'll find that template here or in your pink packet if you're in my class. And you'll see it listed right over here. So I want you to use that as a reference guide. I'm not going to walk you through it all. Instead, I'm going to go right into the problem that is on our notes. This is on page 23. So if you find page 23 of our notes, we're going to be covering page 23 and page 24. So let's read through the problem and kind of work through this part together. Get your pen out and we'll get started. Question, are teenagers going deaf? In a study of 3,000 randomly selected teenagers in 1998 through 1994, 15% showed some hearing loss. In a similar study of 1,800 teenagers in 2005-2006, 19.5% showed some hearing loss. Do these data give convincing evidence that the proportion of all teens with hearing loss has increased? Now, first of all, do we have some evidence that it increased? Absolutely. It raised from 15% to 19.5%. So we know that there has been an increase. Is it convincing that the proportion of all teens has increased? And that's going to require a two-sample z-test for the difference in the two proportions. So how do we set up our null and our alternative hypotheses? Well, we're trying to figure out, is there a difference? So we want to test P, and I'll call it P1 minus P2. So what we're going to say, first of all, is there a difference? Has it increased? So I'll say, well, it's P1 minus P2 to start with, there'd be no difference. So you put equals 0. That's the null. 0 is the null, right? The null hypothesis is no difference. So we want to put 0 in this subtraction one in these type of problems. The alternative, well, it depends on the what you define the P1 and P2 as, but the question says has increased. So I want to know, is that going to be a larger proportion when I subtract these two, provided that the higher one is being subtracted first. So I want to test to see, is that difference greater than 0? And so let's define P1 and P2. Now P1 should be the larger proportion in this case. So P1 will be the true proportion of, well, I'm going to use my higher number. So teenagers in 2005 to 2006. That showed hearing loss. So I'm going to use my 2005 to 2006 data as my first one because I want to subtract that and and test it bigger than 0. That means P2 is going to be the true proportion of teenagers, and that year was between 1998 and 1994. That showed hearing loss. Now the question, nowhere in here does it say there is an alpha level. So default alpha level I like to use is 5%, but you can certainly you can lower that if you want. Depends on the type of test you're running. We'll get more into that in our next lesson. And let's write our p hats here. So first of all, our individual p hats are, well, P1 in this case is going to be p hat 1, right over here, is 19.5%, so 0.195. And p hat 2, that's going to be 0.15. So that was given to us in the problem. You can jot that down. That's going to be helpful for you. We've defined our parameters and we've did our hypotheses. We've stated our alpha level. That's all you technically need to do over here. But I want to go over here for a moment and I'm going to talk to you about this PC that you're going to come up and see for a minute. When you pull out your formula sheet for this class, you're going to notice that under the standard error for two populations, for the difference in two proportions, you have this PC thing going on. And that occurs when the two proportions are assumed to be equal to each other. So when we're doing a test, we assume there's no difference. We assume they're equal to each other. So we actually are going to calculate this thing called PC. And that's your pooled proportions. Now, what is that? Well, it's basically a weighted average of your two proportions. So let's lean into what we have over here. We have 19.5% showed some hearing loss of the 1800. So this would be like your N1, and then of the 3000, that would be our second one. What I'm going to do is I'm going to use these sample sizes and these proportions and calculate basically a weighted proportion so that we assume they're equal to each other on average. That's going to look like this. Our number of combined successes divided by our combined sample size. So our combined successes would be, in this case, N1, which is 1800, times 0.195. I'm going to add that to my N2, which is going to be 3000, times 0.15. So remember, your N1 was 1800 from the problem, and your N2 was 3000. So what's going to happen is we're going to divide that by the total sum of your populations added together. So your samples added together. So 1800 plus 3000. What it does is it gives you not an average of these two percentages, but a weighted average. So it'll basically, it's kind of like an expected value for your average. It's going to lean a little bit more toward the one with a higher population or sample size because there are more in this one. So if we combine those together, you're going to get the following. You have the combined successes, 1800 times 0.195, which is 351, 3000 times 0.15, 450. So I'm going to do 351 plus 450. And that's going to be divided by the 1800 plus 3000, which would be 4800. But I'm going to just be lazy and put it in parentheses and divide by those. And so my weighted average, my pooled sample proportions, this stands for combined. That's going to be 0.167. I'll round that to 3 decimal places. So 0.1668. It's okay to say about 0.167. So you'll see it's a little bit closer to 0.15 just because there are so many more in there. But that is your assumed weighted average between those two. That's going to come into play a little bit later. So I wanted to teach you that right now. Now, as we're going through this, we're still going to check our three conditions. We're going to name our procedure. This is a 2-sample z-test for P1 minus P2. You can also write that in the state part, which I prefer to do. And we're going to do our random, independent, and large counts. So independent random samples. Were these samples independent and random of each other? Well, it looks like up here it says 3000 were randomly selected. In a similar study, 1800 teenagers, similar, I would assume that the same thing went on here. So that's also going to be random here. And I wouldn't assume these studies had anything to do with each other because I think teenagers in this era would not be teenagers over here. So they're independent of each other. So we can say both samples were randomly selected. Good enough. Now let's check the 10% condition. Can we assume that 3000 is less than 10% of all teenagers in that era? And 1800 is less than all 10% of teenagers in that area? For sure, right? So we'll say 1800 and 3000 are both less than 10% of all teenagers. These samples are independent of each other. It's kind of important to include that because we don't want them to be interacting with each other. So while it's assumed to be true, we want to write that. Now, as far as doing the large counts, we still want to make sure our large counts are at least 10. That's where the PC comes into play. And the reason we use PC is because we can't use 0 as a proportion where, the difference is that, well, the assumption is there's no difference. But we don't have any numbers to work with. Do you understand? So I can't just like randomly make up, a number in between them. So I'm just going to use the weighted average. And that's what this PC is going to give us. So our large counts, what we'll do is we'll do N1 P hat C, N1 1 minus P hat C. And then we'll do N2, but we're still going to use P hat C. So we're going to use the same proportion for these. And then we're going to do N2, and we're still going to use P hat C, or 1 minus P hat C. So we want to get all 4 of those numbers. And our N1 in this case here was 1800. So I'm going to go ahead and write 1800. And I'm going to times that by this 0.167. I'm going to do the same thing here, 1800 times 1 minus 0.167. And I'm going to use my 3000 for N2. And I'm going to use the same pooled proportion because they're assumed to be true. So we don't want to change them. 167 and 1 minus 0.167. And of course, those are all 4 of those should be greater than or equal to 10. So we'll just double check that in the calculator and calculate those numbers out. We still got to calculate them. And you'll notice that's going to be about 301 and 1499. I'm just going to round, but you can use the decimals or 300 and something. It's not a big deal as long as you're getting numbers consistent with what you're using here. And you're going to go down here and do the same thing. So 3000, 0.167, 501, and 3000 times 1 minus 0.167. And there's your 24.99. Plenty big enough to use a normal curve around there. So we are good to go in that regard. But PC is going to be your go-to for these. When you're doing your large counts, you're going to want to do your PC. Now, I got a trick for you here. This is tedious to calculate that. So I'm going to go ahead and show you how to run the test in your calculator first, so that way you can get that number and directly throw that in here. So if you decide not to do all that work to calculate PC, that's okay, because what you can do is you can go to Stat and go to Tests, and this is a 2-sample z-test. So this is going to be a 2-prop z-test. Don't look over here. This is a 2-proportion z-test for P1 minus P2. And what we're going to do is we're going to input our counts. So we're not given the number of people out of the 3000 that had hearing loss. We're given the percentage. So I'm going to do 0.15 times 3000. Oops, let me go in the right order. I'm going to do 0.195 times 1800. And it's going to calculate that for us. That's at 351. And then over here, you're going to do 1800 for the N. For X2, we're going to do 0.15 times 3000. And 3000 for your sample size. And we want to test to see that it's increased. So I'm going to go ahead and do larger than. I'm going to go calculate. Excuse me. One thing you're going to see here, you're going to see your Z and your P value. You're going to be given your sample proportions. And right here, it'll give you that, it just has P hat. Now, P hat is your PC. So there's a little, that right there is your pool proportions. That number is the same right there as what we calculated here. And so if you wanted to just calculate that running the test, now that you have the numbers, you can jot them down. And I am, I'm not going to sit here and go through all the work on there. This is a two sample z-test. For the difference in the proportions. You would have to calculate this out, but look at, you're given the z score right here anyway. So z is going to be equal to 4.04, I'll say 4.048. Your p-value, that's the next thing. That is right there. And then that's set e -5. So remember, there's going to be 4 zeros to the left of the 2. So your p-value is 0.0000258. And then you can list out, if you want to, your p hat 1, p hat 2, and your pooled proportions. So if you haven't labeled them already, that would be okay to write them here too. But you can get that PC right there, 0.166875, and use that for your large counts. You must use that to calculate your large counts. So you can get that from your 2-prop z-test. And then finally, on our conclude, since the p-value of, well, what is our p-value? 0.0000258. Obviously, it's very small. Well, how does it relate to our alpha? I used 5%. We could have even lowered that to 1% and still made the same conclusion. So since it's less than our alpha of 0.05, well, what do we do in this case? We reject the null hypothesis. There is convincing evidence that the true proportion of, what are we talking about? Teenagers, true proportion of the difference in hearing loss. The true proportion of hearing loss in teenagers Now, what did it do between this and this? Increase. The true proportion of hearing loss in teenagers has increased from this set of years and that set of years to that study. Obviously, you're not going to be given some words to fill in the blanks here, but you want to write something to give the point across for the context. So always link your p-value to your alpha. Notice I didn't put any of the work here. Here's what that work would look like. All right, I have it written out here. I want to point out where on the formula sheet you would find that. So over here, you're going to see this formula for the standard error of the difference in the 2 proportions. You're going to have your pool proportion, 1 minus your pool proportion, 1 over n1 plus 1 over n2. It's all right there, and it gives you the formula for the pooled proportion as well. I plugged them in right here. This right here is the difference. So this is like your p hat 1 minus your p hat 2. And so you calculate the difference, subtract 0 because remember the null is no difference. And if you do that calculation carefully, I did the standard deviation first because it's so convoluted. And I did the top part and I divided by this and I got 4.0467. And it's pretty close here. I mean, I rounded a little bit, so it's not quite what your calculator is going to give you, but it's close enough. 4.048 is close to 4.047, so it's not that big of a deal. And then finally, if I did a normal CDF, since I want to go greater than, I would do 4.047 to infinity. And I get my p-value of 0.0000259 instead of 8. Not a big deal. All this to say is, yeah, you're going to make mistakes doing this by hand unless you're very careful and want to spend a lot of time doing that. So when you do your test, just do that, okay? Name the test, report that, get your p hat c so you can use that for your conditions and you're good to go. Okay, this is a 2 sample z-test for p1 minus p2. All right, so these are the important ideas. Again, these are the same type of things that are be listed on your pink template. So what I want you to do is read through this problem, try it on your own, pause the video, use the pink template in the notes to help you construct the 4-step plan for constructing this interval. And then I'll have it worked out and I'll go over it once you unpause it. All right, here we go. I have this worked out. Let's take a look at kind of some of my annotations on here. Let me zoom out just a little bit. And I cannot fit this in the space below, so I simply just did a brand new page of it. So what we want to do is we want to read through this first. A researcher conducted a medical study to investigate whether taking a low-dose aspirin reduces the chance of developing colon cancer. As part of the study, 1,000 adult volunteers were randomly assigned to one of two groups. Half the volunteers, so 500, were assigned to the experimental group that took a low-dose aspirin each day, and the other half were assigned to the control group that took a placebo each day. At the end of the 6 years, 15 of the people who took the low-dose aspirin had developed colon cancer, and 26 of the people who took the placebo had developed colon cancer. At the significance level, alpha is 0.05. Do the data provide convincing statistical evidence that taking a low-dose aspirin each day would reduce the chance of developing colon cancer among people similar to these volunteers? So remember, for experiments, we want to look for cause and effect, and this is the work that gets you to determine if something is statistically significant. We do a test. Now we can see that 15 of the 500 developed cancer when they took the aspirin, whereas 26 of the 500 developed cancer when they did not take the aspirin and they had the placebo instead. So you can see that we have some evidence to conclude that this is a reduction, but is there enough evidence? Well, that's what a hypothesis test will be set up for. So we're going to name the test. This is a two-sample z-test for P1 minus P2 because there's two different proportions. We want to set our null hypotheses that there is no difference, so we say 0. In alternative, we say less than 0 in this case, because if I'm defining P1 as the true proportion of the aspirin group, we're going to notice that that number is smaller than this. And since we're looking for a reduction, we're looking to reduce, we want this minus this to be a negative because we want to see that this, we're testing to see if this is smaller than this. If we reverse the order of the direction we subtracted, then we'd have to switch this to greater than 0. So because I defined P1 as the aspirin group with the smaller one, and I'm looking for this to be smaller, I want this to be in the negative. That's what I'm trying to test. We're going to do the alpha as 0.05 because it says so right here in the problem. Now, I have the work showing the pooled proportions. Each group is going to be 500. So I calculated the percentages, 15 out of 500, 3%, 26 out of 500 is 5.2%. Hopefully you got those same too. And I put that into our pooled proportions formula, which you will find up here on the formula sheet. So it's x1 plus x2 over n1 plus n2, but you can also just basically multiply the n1 p1. So that 500 times 0.03, that's going to get you back to 15, and that 500 times 0.052 is going to get you back to 26. So if you just put 15 and 26 there, it's the same thing, right? So 15 out of 26 divided by, well, that's just 1,000, and that should get you the 0.041. And there's your pooled proportion. So real quick here, before I do the conditions, if you want to run the test, you can get that pooled proportion just to make sure you have that. So this is a stat test, not 5, this is 2-prop. So we're going to go to 6, 2-prop z test. And this is the entered numbers that you'll have in 15 out of 500, 26 out of 500, and less than. And I'm going to go down to calculate. Don't do draw because the draw won't give you the pooled part. And I would jot these down in the do part so that way you have them. Your z-score should be negative 1.754. Your p-value is 0.0396 or 97. Here's your two individual proportions and your pooled proportion. Remember, this is your pooled up here, and that's going to be the number we use right there. And your two sample sizes, each treatment group 500. So you can use that to check your conditions. We're going to state both treatments were randomly assigned. We're going to say each treatment group is independent. 10% doesn't apply here because these were volunteers, so we're not sampling from a larger population, so that's not necessary. Just state that they're independent of each other, and that's good enough. When we're doing your large counts, remember to use your pooled proportion. Now, it just so happens these will be the same numbers because these are equal sample sizes. So since those are all going to be the same, you're really just calculating, two things twice. And so both sets of those are both going to be greater than 10. So it is safe to use a normal curve. And when we're calculating our z-score and random condition, or our sampling distribution for our statistic, we can use a normal curve here. Now, I didn't get into all the work here because frankly, it's not really necessary. So what I'm going to do is I'm going to list that I stated the two proportion z-test from the calculator. I'm going to write down my z. That's the important part. And I'm going to write down the p-value, 0.0397. And I'm going to add a curve on here. So what I'm going to do is to satisfy, that are we using a normal curve? We're going to say 0. We're going to go to negative 1.75. Remember, these are standard deviations. So this is one standard deviation. This is negative 1.775. And I want to know the likelihood of being at that value or more extreme. So in this direction here. And it turns out it's about 4%. You can get that. Let me do N01. You can get that also by doing the draw feature. So I'm going to go back and do it one more time with the draw. And that's what I showed here on there. So I would like you to draw the curve on there and just kind of label your number of standard deviations away from the mean and shade in that appropriate direction. And there's your p-value right there. Not necessary to do the formula on there. It's too much risk making a mistake on it, to be honest. So let's finalize this. Since our p-value of 0.0397 is less than our alpha, we're going to reject. We have convincing evidence to conclude that the aspirin does reduce the chance of developing colon cancer among people similar to these. And so we've conducted our test. We got a small p-value. We've linked it to alpha. You've done our conclude part. So that is this problem here. And if anything, if you have any questions on it or any questions on your assignment, please ask, and I'll try to help the best I can. Thanks for watching.